Hey everyone, it's me, Dr. GB. So I'm hanging out here in student hours and nobody's here. So that's okay. I'm going to take this time to go over and make a video to go through some problems from our in-class time to help out and maybe anticipate some student questions. Okay, so at the beginning of today's class, we spent a lot of time talking about intermolecular forces and solubility. So let's take a look at some Henry's Law questions first. All right, so for Henry's Law is talking about the solubility in gases. All right, so what Henry's Law says is that the solubility, which has units of molarity, is equal to our Henry's constant, K sub H, times the pressure of the gas. Alrighty, so a larger value for solubility means that our compound is more soluble. So having an increased Henry's constant and an increased pressure promotes an increased solubility. Now, you may be wondering, something I'm going to ask you to talk about probably is talking about the molecular basis for why one compound may have a bigger Henry's law constant than another. So for instance, if we compare CO2 to, let's say, NH3, NH3 would have a larger Henry's law constant than CO2 because NH3 is polar due to its geometry, whereas the dipoles on CO2 cancel out, leaving out an overall nonpolar molecule even though the individual bonds are polar, all right? So this Henry's law constant is linked to the structure and polarity. And remember, the stronger IMFs, so the bigger charges on the molecule, alrighty, the larger the Henry's law constant and the more soluble the compound. So most of the Henry's law problems you see, if I give you a Henry's law problem, are going to be using this equation where I'll give you the solubility and the pressure and you have to solve for the Henry's law constant, or I'll give you one of these two and you have to solve for the solubility, or maybe I'll give you the solubility and the Henry's law constant and you'll have to solve for the pressure. Okay, so let's go ahead and let's look through some other types of problems. Alrighty, so what I'm going to do is I am going to work through a problem where we have a volatile solvent and we add in a non-volatile solute. We'll start there. Okay, so we're going to go ahead and I am going to do, let's do 2F. Alrighty, so at 2F is asking, what is the vapor pressure of a brine solution? Okay, so brine is used to like treat meat before we eat it, alrighty, or if you eat meat. What is the vapor pressure of a brine solution? So brine is H2O, water, plus NaCl, salt, okay, where we have 3.00 kilograms of water, and then we have 250 grams of NaCl. Okay, so NaCl is a solid, all right, so it's going to be non-volatile. But H2O is, and this is at 100 degrees Celsius. So what this problem is, so we know that water has a vapor pressure on its own. Alrighty, and so at 100 degrees Celsius, at 100 degrees Celsius, we are at the boiling point of water, and so our vapor pressure of pure water will be 1 atm. So we learned an equation today where if we have a volatile solvent plus a non-volatile solute, this is a colligative property, alrighty, or our vapor pressure of our solvent is affected by the amount of the solute. So we can calculate the vapor pressure, all right, of our modified vapor pressure is equal to the mole fraction of the solvent times the vapor pressure of our pure solvent. And so what we have to do here is we have our vapor pressure of our pure solvent, that's 1 atm. We don't have is our mole fraction. So what we have to do is we have to do moles of H2O over moles of H2O plus moles of NaCl. And that's exactly what we'll do. So for water, we have 3 kilograms. We convert from 1 kilogram to 1,000 grams. And then we know that the molecular weight of water is 1 grams per mole. And that will give us a whopping 166.67 moles of H2O. For sodium chloride, we have 250 grams. Our molar mass is 58.44 grams per 1 mole, and that gives us 4.28 moles. So what we're going to do here is our new vapor pressure, when we add in that salt for that brine solution, is going to be 166.67 over 166.67 plus 4.28. So that's our mole fraction of solvent, times 1 ATM, which gives us 0.97 ATM. All right, so if we have 3 kilograms of water and we add in 250 grams of salt, again, it's going to lower the vapor pressure just a little bit, but it's a big enough difference that we can calculate it. Okay, so for G and H, we are approaching the problem in the exact same way, except for G, instead of sodium chloride to have brine, we're using sucrose. And then for H, we are using glucose. So in both of those cases, we will see how sucrose and glucose lower the vapor pressure of water. Now, we don't just have to do water, we could use another solvent. So we could do benzene, toluene, anything else. So let's move on to our other problems. Okay, so we move on to problem 3. Alrighty, so for number 3, we're going to see 2 types of problems, okay? And so the first type of problem that we're going to see is when we mix 2 volatile liquids, okay? All right, and so what we're going to do is we're going to see what is the vapor pressure of the resulting solution. So I'm going to go ahead and I'm going to do 3. I'm going to do 3A, okay? So and I don't have the temperature. Whoops. Okay, it's 20 degrees Celsius. Okay, so 20 degrees Celsius, our vapor pressure of ethanol is 45 torr. And note that ethanol has a molar mass of 46.07 grams per mole. And our pressure of methanol, I'm going to abbreviate as MEOH, has a pressure of 92 torr. Alrighty, and that's methanol has a molar mass of 32.04 grams per mole, just FYI. Okay, so what this question is asking is what happens if we mix 25 grams of ethanol and we add 75 grams of methanol. Excuse me, it's the other way around. 25 grams of methanol and 75 grams of ethanol. What is our total, our P total? Okay, so what happens here is this is where we have one of our applications of Rayleigh law, where our P total, and this is an application actually of Dalton's law of partial pressure, where our total vapor pressure is equal to the vapor pressure of ethanol plus the vapor pressure of methanol. Now, we don't have pure ethanol, we don't have pure methanol, so we have to account for the others or their effects on each other. So, that is equal to, we have to do the mole fraction of ethanol times the vapor pressure of pure ethanol plus the mole fraction of methanol times the vapor pressure of pure methanol. Alrighty, so we have the mole fraction times the pressure when it's by itself. Alrighty, because again, what's happening when we mix them together is we're swapping out moles of one for moles of another. So we have to account for that in our new vapor pressure. So what we're going to have to do is we are given these values. So the vapor pressure for pure ethanol is 45 torr. Alrighty. And then the vapor pressure of pure methanol is 92 torr. So what we have to do is we have to solve for what our mole fraction is, alrighty, for each. And the way to do that is we have to get our moles, which we have what we need. So our moles of methanol are going to be equal to 25 grams of methanol. And then we convert to moles by dividing by the molar mass. Alrighty, so that is 32.04 grams per 1 mole. And that gives us 0.78 moles of methanol. All right, our moles of ethanol We have 75 grams. We divide by our molar mass. And that gives us 1.63 moles of ethanol. Okay, so now we have what we need to go ahead and substitute into our equation. So I'm going to go ahead and erase that, alrighty? And we can actually go ahead and we can calculate our total moles, alrighty? Because that's equal to 0.78 plus 1.63, which is equal to 2.41 total moles. So our mole fraction of ethanol is moles of ETOH over total moles, whereas our mole fraction of methanol is equal to moles of methanol over total moles. And so we'll go ahead and we'll incorporate that into our equation. So we calculate the P total. So moles of ethanol, we have 1.63 moles of ethanol divided by 2.41. And again, our moles are going to cancel, and that's a fraction, times our vapor pressure, which is 45, plus our mole fraction of methanol. Okay, so that's 0.78 moles over 2.4 moles times 92. Okay, so that comes out to, all right, now I'm going to go ahead and I am going to be a little messy here. I'm going to draw an arrow going down, and I'm going to say, okay, so 1.63. All right, so that's 0.68 times 45 plus 0.32 times 92. All right, so that's 30.6 plus 29.4, and that gives us 29.4 plus 30.6. That gives us 60 torr. Alrighty, so that's how we got to there. And again, the work is in the thing. I just wanted to walk you through my logic. Okay, so I'm gonna go over one more type of problem. Okay, so B and C look exactly like that, are very similar to that. D is a little bit different in that what I've done is I've actually given you the mole fraction of benzene, which is equal to 0.30. The mole fraction of toluene is going to be equal to 1 minus the mole fraction of benzene, which, spoiler alert, is going to be 0.7. So if we solve for P total is equal to 0.3 times the vapor of benzene plus 0.7 times the vapor pressure of toluene, and in that case toluene is given to you, so it's 533 millimeters Hg. And the kicker here is a benzene toluene solution has a normal boiling point of 98.6 Celsius. The vapor pressure, what is the vapor pressure of pure benzene at 98.6? Okay, so what the key there is normal, alrighty, and so if that's our key, that at 98.6 degrees Celsius, we are at 1 atm or 760 millimeters Hg. So we can substitute in 700 millimeters Hg for P total and then use that to solve for the vapor pressure of pure benzene. Okay, then I'm going to do a freezing point problem. Alrighty, I'm going to do a freezing point depression or boiling point elevation. And again, how this works is we have our change in temperature of our boiling point or our freezing point, and that's equal to the molality of the solution times the I, which is the dissociation factor. I think it's a dissociation. I'm blanking on the name, but that is an indication of how many ions it forms in solution, which is linked to whether or not it is an electrolyte or a non-electrolyte, times our K, B, or F, or our freezing or boiling constant, depending on what we're looking at. So I'm going to go ahead and I'm going to work through one of these, which we're going to look at E. Alrighty, so E is what is the boiling point of a 1.962 molal solution of NH4NO3 given the boiling elevation constant is 0.52 degrees Celsius per molal. Okay. So we look at our equation, our change, and this is boiling, so our change in our boiling point is equal to our I, which again is the number of ions really that are formed in solution, times our molality, which we know is 1.962 molal, times our boiling point elevation constant, which is 0.52 degrees Celsius per molal. Okay, so we've got our molal, we've got our boiling points, our freezing, our boiling point elevation, and we're looking for our change, but we also need to find out our I. So our I tells us our number of particles in solution. So if we have a non-electrolyte, all right, so like sucrose, something that doesn't split up in solution, it's going to have an I equals to 1. However, NH4, NO3 splits up to make NH4 plus and NO3 minus. We learned in our solubility rules that nitrate, compounds that contain nitrate are always soluble. So in solution, we are going to have 2 molecules. So our I is going to be 2 here. So what we can do is we can solve for our delta TB. So our delta T sub B is equal to 2 times 1.962 molal times 0.52 degrees Celsius per molal. All right, our molals cancel, and we end up with a delta TB of 2.03 degrees Celsius. Now, what the implication here is, this is asking for what is the boiling point of the solution. And this is assuming we're adding water plus NH4, NO3. So what this is telling us is that our old boiling point of our BP of pure H2O plus 2.03 degrees Celsius, which is our change in temperature for the boiling point, gives us our boiling point of H2O plus ammonium nitrate, which is going to be 102.303 degrees Celsius. Alrighty, there we go. Then finally, if I take a look at our other compounds, these are related questions. And so for F, again, is going to be a similar one where we have KCl, and so KCl is going to dissolve into K plus and Cl minus. For our other ones, G and H, again, a similar approach, but cinnamaldehyde and carvone are not ionic compounds. They're not electrolytes, so they're not going to split up. So we can assume an I of 1 there. It's just going to be 1 molecule. And for G, we are solving for the delta TF, or the freezing point. And again, it's cinnamaldehyde dissolved in water, so you're going to find the change and then apply the change to the freezing point. That's in benzene. Whoops. So you're going to apply the change to the normal freezing point of 5.5 degrees Celsius. And then for H, it's carvone dissolved in carbon disulfide. So you're going to solve for the boiling point elevations. You're solving for the change there. But you could add or subtract that change. You would add that change to the boiling point to the boiling point if we knew it. And for our last thing, we're going to talk about deviations from Rayo's law. So with Rayo's law, we make the assumption not that intermolecular forces don't happen between molecules, but rather all the intermolecular forces between all molecules are the same. So if we have A and B, the intermolecular forces that occur between B and A are equal to each other, and they're also to the intermolecular forces that occur between B and A. All right, that's the big assumption we make. So when we think about Rayo's law, what we have to remember about vapor pressure is we have a situation where we have molecules A and B hanging out in solution versus just A and then just B, okay? We have to remember that we're going to have some molecules in solution, and then we're going to have some molecules in vapor, okay? We have to remember that we have intermolecular forces present in the liquid form, but we don't have any IMFs present in the gas phase, okay? So when we go from liquid to gas, we're going through that process of breaking IMFs. So if we have a mixture of A and B versus A and B, so let's say, for instance, we have a mole fraction of A is 0.5, we have a mole fraction of B is 0.5. When we have, so for instance, if we have a solution where we have our P VAP naught of A versus our P naught VAP of our pure B, alrighty, so we've got our vapor pressures that correspond to our pure solvents. If we have a situation where we mix them together and now we have half of it being A and half of it being B, all right, our vapor pressure for A is going to be lower because it's going to be 0.5 times P naught of A, whereas our vapor pressure of B is also going to be lower because, again, we're going to have half of B versus if it was pure B. Now, the question may become, how does the P total turn out? Well, that depends on the vapor pressures of PA or PB. So the P total is going to be greater than the P naught of the one that has the smaller vapor pressure, but it's going to be smaller than the P naught of the one that has the larger vapor pressure, if that makes sense. Okay, so now thinking about deviations from ideality. So again, if we make the assumption that the interactions between A are equal to the interactions between B, are equal to the interactions between A and B, as we increase, as we decrease our amount of A, our vapor pressure of A will decrease. As we increase our amount of B, it will decrease. Where the deviations from ideality come in is when we can no longer make the assumption that all of the various intermolecular forces are equal. So if the interactions between A and B are greater than A and B, or if the interactions between B and A are greater than the interactions between A and B and B. So let's walk through these two cases together. So remember, this is really important to remember that for vapor pressure, all our molecules on the liquid form have intermolecular forces between them, but the gases don't, all right? So if our intermolecular forces are stronger, our liquids are more likely to stay in the liquid phase than they are to go into the gas, alrighty? So if we have a situation here on the right, all right, our new IMFs are stronger than the IMFs are between the individual liquids. So what this means is that our molecules are more likely to stay in the liquid and form IMFs. All right, so they're more likely to stay in the liquid form and form IMFs with each other. All right, so what happens is if they're more likely to stay in the liquid, that means we're going to have fewer number of molecules in vapor than the pure solvent. Alrighty, and so this is what we call a negative deviation. All right. So stronger IMFs means we're going to have more in the liquid, less in the vapor, which means we're going to have a lower vapor pressure than we would have predicted if all the forces were equal. Okay, if we have a situation where our intermolecular forces are stronger on their own, all right, so original IMFs are stronger. So what that means is that the liquids don't want to mix, alrighty? So what's going to happen here is the molecules will go into the gas form rather than IMF as liquids. Alrighty? Or the vapor pressure is higher as a mixture than we would have predicted based on the pure vapor pressure of the individual components. Okay, so the question becomes, how do we know what's going to do what? Okay, so for an ideal situation, the molecules have to be basically the same. And frankly, our closest examples of ideal, they're going to be ones that are non-polar, okay? So these are molecules that are small, they're usually small, they're about the same size, and they all LDF with each other. So this is like the difference between benzene and toluene, which are one molecule apart, or methanol, CH4, versus ethanol, CH3, okay? Or, oops, that would be, yep, CH3. Okay, so, and that's where basically, okay, so what's a situation where we have, and if we look at our homework questions, our in-class problems that we worked through, all right, there's a couple examples where we would have ideal solutions that would be pretty close to ideal. And so 2 examples of molecules that would act ideally would be carbon tetrachloride and silicon tetrachloride. All right, so CCl4 and then SiCl4. And the reason that would be is because they're both non-polar molecules and they're both about the same size. So there's not that big of a difference between carbon and silicon, all right? So they're gonna be close to ideal because they're very similar in composition and they can both only do LDF. The other one that would be ideal would be CH3CH2Br and CH3CH2I. Again, that bond between C and Br and C and I is, I think it's either almost not non-polar or like only very slightly polar. And then all of this over here is non-polar, and bromine and iodine are about the same size. So these molecules are about the same size. They primarily LDF. So again, these will be ideal. So let's talk about the other option. Okay, so our negative deviation, again, negative, when we talk about negative versus positive, it's always referring to the vapor. So negative means less vapor. So stronger IMFs would lead to less vapor. So some examples of pairs that would lead to a negative deviation. Okay, so H plus and HCl. So HCl and H2O. Okay, so HCl on its own is ion-ion. H2O is H bonding. When we bust these up, all right, we get H plus and Cl minus. And then what's going to happen here is our water can ion dipole with our H plus and Cl minus ions. So this will be negative because on our own water can only H bond, but in the group water can ion dipole. Again, we could debate, is it more advantageous for HCl to be a salt or be with water? We could have that discussion. We don't have all the tools to have that discussion. So for the purposes of the class, if one of them benefits from mixing, it's good enough for us. So in this case, water is benefiting from ion dipoling with HCl, so we're good to go. Okay, another example would be dimethyl ether and water. Alrighty, so we have dimethyl ether and water. Right, so water here on its own, water has that partial negative, partial positive. We have a partial negative, partial positive here. Water can H bond on its own. Ether can ion dipole on its own. However, we put them dipole on its own. We put them together, ether can now hydrogen bond when it could only dipole before. So this is again going to be negative. Alrighty, so that's a big deal. Now, let's think about other situations. Alrighty, so for instance, if we have a big one here is ethanol and water. So with ethanol, we have H3C, CH2OH versus water, all right? So this is where the difference is. So both of these have O's attached to H's, so both of these can H bond, all right? So when we mix them together, we're not really having any benefit because ethanol and water can still hydrogen bond with each other. However, water can make fewer hydrogen bonds with ethanol than it can with itself. And so this would be a positive deviation. Similarly, if we were to look, we'll also see a positive deviation if you mix a polar and a nonpolar object. And we see that with acetone and carbon disulfide. Alrighty, so acetone and then carbon disulfide. Alrighty, so acetone can dipole with itself. Carbon disulfide is linear, it's linear geometry, and it's nonpolar, so it can London dispersion force with itself. If you mix acetone and carbon disulfide, what's going to happen is that acetone is going to break dipole-dipole bonds to make weaker dipole-induced dipole bonds with carbon disulfide. And so those two are not going to want to mix. All right, we don't want to break those dion-dipole interactions, which are stronger than the new interactions that will be formed with carbon disulfide. So what's going to happen is acetone is going to go into the vapor phase rather than interact with carbon disulfide, and vice versa. So this would be another example of a positive. All right, so negative happens when at least one of the parties benefits from forming those new intermolecular forces, and a positive deviation happens when one of the molecules is hindered or hurt or makes weaker interactions as a result of mixing. I hope this helps.